How, when, and why do you think the universe we live in today was created?
That's a complicated philosophical question. The universe wasn't created, the universe just is, like the number 2. Even though we're made of different stuff at every moment in time, we have the perception that it's still the same us a second, a minute later. The current round of neural network, large language model, AIs, are pretty similar in architecture to brains. The search for something beyond to explain the sort of the human experience is one that's existed forever.
According to you, does free will exist, or is it an illusion?
We can't know in advance what we're going to do. Now, one day it'll be possible to kind of read out the states of all the neurons in our brains and so on, and to compute what are we going to do next. When you have enough matter in the universe, you end up inevitably forming a black hole. One feature of black holes is that time stops in a black hole. So normally time is just running forwards and the universe is computing its next state and so on. But in the center of the simplest kind of black hole, time just stops. So in terms of computation, it's like there was a thing you were computing and there was no more rule that could be applied to know what to get next.
Stephen Wolfram, it's truly an honor to have you here. Only a few thinkers have redefined how we understand reality, computation, and intelligence the way you have. I've been really looking forward to this conversation, and I can't wait to explore the ideas that have shaped your journey.
Thanks.
From a computational standpoint, how, when, and why do you think the universe we live in today was created?
That's a complicated question. That's a complicated philosophical question. I mean, if you say something like, why was the number 2 created? That's not really a meaningful question, because the number 2 isn't really something that's created. It's something that just is an abstract construct that is. And one of the things that's sort of come out of a bunch of science that I've done is that in many ways we can think about the universe, or something of which the universe that we perceive as a part, something related to the universe, is an inevitable thing like the number 2. And this is a thing that I call the rulad. And it's kind of a long story how one gets to this, but the end result is that there's this kind of construct that we can think of as kind of the entangled limit of all possible computational processes. That thing is an inevitable, has to abstract kind of thing. The thing that is not so, there's no question about whether, can it exist? Does it exist? It's an abstract thing. In some sense, you can't ask whether it exists. It's just a thing like the number 2. Now the issue is, but we are observers of this thing. It is not as self-evident that we exist, but to us it is self-evident that we exist, because that's why we're even asking the question, so to speak. And so then the issue is, if you have an observer like us, what do they perceive of this rulad object, which is this inevitable entangled limit of all possible computations? And the thing that we know, that sort of one of the discoveries of the last few years that I've been working on, is that for observers who have characteristics like us, it is inevitable that what we observe of our universe must follow laws that are like the laws of physics that we know that we perceive our universe to follow. So in some sense, this question of the universe wasn't created, the universe just is, like the number 2, but it is our sort of perception of it is something that comes about because of our nature as observers. We observe the physical laws we do because we are observers of the kind we are. If we were different kinds of observers, if we were some kind of alien something or other, we would potentially perceive different laws of physics, perceive different laws to be operating in our perceived universe.
Even other species, everybody perceives the world in a different way. Like, we're perceiving the world in one way as human beings, but a snake would perceive, according to himself, he would perceive the world in a totally different way than we do.
Well, right. I think the thing that in kind of my way of thinking about this, we can think about, people can be in different places in physical space. There's also this concept of rulal space, which is kind of the space of possible ways that you can perceive the universe. And we can think of different minds as being kind of dotted around in rulal space. And so, for example, humans who've learnt things in similar ways, they're pretty close in rulal space. The snake is much further away. When we get to things like the weather, which has all of these processes that go on in it, much like we have all these processes that go on in our brains, its way of perceiving the world, if we can think about it in that fashion, is still further away. But it's sort of, there's an interesting question. What is the perception of the world by what laws of physics do, the whales have, or the snakes have, or whatever? I mean, one thing that is pretty clear is, snakes have some funky sensory organs. They have a bunch of infrared sensory organs and so on, that are different from ours. And, the things that we describe the world in terms of, snakes, probably, if snakes had a language, the words snakes would have in their language would be quite different from the words we have in our language. And the kinds of things about which snake physics would talk would be somewhat different from the things about which human physics talks. Less different than what sort of if the weather had a language for talking about physics, its view of physics would be still very different, much more different even than the snake's view of physics, so to speak.
Yeah, no, I very much resonate with that. You know, also, if the universe is ultimately a computation, what does that say about our place within it? Not just as observers, but as participants. Are we living in a virtual reality simulation? I know Elon Musk has stated that he possibly believes that.
Well, I think that's a philosophical muddle, because in a sense, to say we live in a simulation kind of implicitly says there's somebody running the video game. And somebody decided to, in modern times, you don't put a video game cartridge in, but somebody decided it's this universe, not another one, right? And that's kind of the simulation idea is the idea there is sort of the overintelligence that is puppeteering our universe, so to speak. And that's so you again have to imagine that there's sort of an over universe that's controlling our universe. So one of the features of the rulad is that's it. That is the limit of all possible computations. There's nothing kind of outside of it. Well, I have to be very sort of strictly correct. I will say that the rulad represents the limit of all possible computations. There is a notion of hypercomputations, computations that can do in fixed time what a computation of the kind that we normally think about would take an infinite time to do. And so, in addition to the rulad, there are an infinite collection of hyperruliads that also, in the same sense as the rulad, exist. But one of the features of that, which is sort of a scientific feature, is there's an event horizon. There's a boundary between the rulad and all the hyperruliads and every hyperruliad and every other hyperruliad. And you'll never know anything outside of your rulad or hyperruliad exists. It's a thing that is its own independent object that has no connection to anything else. So it's kind of and by the way, it's probably the case, I don't know this for sure, but I'm pretty sure that there's a kind of rulal version of relativity that says if you're an observer in the rulad, you observe certain kinds of things. If you're a hyper observer in the hyperruliad, the things you observe will be equivalent to the things that an ordinary observer observes in the rulad. So there's no sense, there's no choice. It's like we're stuck with the rulad, and that's what we're in. Now, the question of how we perceive the universe depends on what we are like as observers. So it's not the idea that there is a sort of an outside entity that's puppeting the universe, so to speak. It's really the opposite way around. It's observers like us observe the universe we observe, that we observe the particular slice of the rulad that we observe. So it's kind of, it's an inside out view rather than an outside in view. It's not, there's an entity outside that is choosing what the universe will be like, and we are merely players on that stage. Rather, it's the universe is inevitably a certain way, and observers like us observe a certain thing within that universe.
Because we are talking about us as observers, I wanted to bring upon the topic of consciousness. Do you think consciousness is computational? And if so, And this is just taking it even further. Do you believe that it could emerge in non-biological substrates? Like, can artificial intelligence possibly become sentient or conscious in the near future?
Consciousness is a very slippery word. I think that, we have a certain perception, internal perception of ourselves, and the question of whether anything else, other than what we internally feel about ourselves, whether anything else is quotes, conscious, is an extrapolation of some kind. We humans are sort of similar enough that what my internal feelings are like, I can well imagine that you have some analog of that. If I look at, I don't know, a waterfall or something, it may have all sorts of complicated computational processes going on, but I don't have immediate empathy for it. I don't imagine that it's like me, so to speak. I mean, if we were to sort of take apart the humans, we'd say, well, there's a bunch of nerve cells and they have electrical signals. There's 100 billion nerve cells in a brain, and they're all doing all these complicated things. And somehow something about that is the thing that causes us to feel the way we feel internally. But we look at some other system, like a waterfall or something like this, it's got all kinds of complicated things going on, just like all those nerve firings of our 100 billion neurons and so on. But it is very different from us. So we don't have that sort of empathetic feeling that it's kind of got that same spark of whatever it is we have, that it's got that same kind of spark. It seems like something very different. Now, in terms of what is sort of the essence of human consciousness, it's sort of an interesting thing, because I think that some aspects of it are sort of critically important to the way we perceive the world. Like one feature of the way humans typically are is we believe that we have this sort of persistent single thread of experience. Even though in our model of physics, for example, we're made of different atoms of space at every moment in time, even though we're made of different stuff at every moment in time, we have the perception that it's still the same us, a second, a minute, whatever later, which is really a funny thing, because it's, in a sense, the substrate is different. It's kind of like if you look at a fluid like water, you have a little eddy in the water. That eddy at every moment is made of different molecules, but yet there's some sense in which the eddy itself is somehow persistent. And it's the same sense in which our consciousness, you might call it, sort of persists, even though the substrate from which it's made does not. I think it's fairly important to human consciousness, the way we sort of perceive things, that we believe that we are persistent in time and we have this single thread of experience. It could be the case we got 100 billion neurons running around doing their thing. It could be the case that we have 1,000 different threads of experience going at the same time. We don't. We humans, in our normal operating conditions, so to speak, we kind of believe that definite things are happening. And that's very important to our perception of the world. I mean, interestingly, in human society, there are, 8 billion of us humans around right now, and we all have this different perception of what's going on. And that's sort of a thing that could be inside a single mind. It could be that we have many different perceptions of what's going on. That just doesn't happen to be the way that humans are built. And, I think that's a special feature of us humans. If we operated differently, we would have a different view of the world. We'd have different laws of physics and so on. So, in that sense, it is an application of the idea of consciousness as we perceive it, which is things like the single thread of experience, that when we think about what laws of physics do observers like us, entities like us, perceive, it is then important that there are certain features which you could say are sort of features of consciousness. One of the things about that view of consciousness is one might have said, consciousness is the pinnacle. It's kind of like there's things in the universe, and there's rocks, and there's rivers, and there's all these kinds of things. And then the pinnacle is, human consciousness or something. I don't think that's really right. I think that all of these different systems are at some level equivalent in the sophistication of the computations they can do. It's just that human consciousness has organized those computations in a way that is somehow familiar to us and we find sort of interesting. It's like there's a different organization of computation that happens, let's say, in the weather or something like this, it's no less sophisticated than what's happening in our brains. It's just less engaging to us as humans because we are sort of the result of a particular process of evolution and so on. We are constructed in a particular way, and we're most interested in things that sort of work the same way we do, like other humans do, and so on.
Yeah, no, that's a very interesting view on consciousness because, and I would love to talk a little bit more about consciousness just because for the viewers that are watched the podcast till this point, we have a lot of audiences that are very much interested in different sorts of philosophies. One philosophy being an example of Advaita Vedanta, where they believe in an ultimate reality and a universal consciousness. According to you, is what do you believe in that, or what would you say to that?
I don't know enough about that belief system, but I think that the idea that somehow, well, okay, so it gets a little complicated. So, one of the things that's sort of in this idea of the rulad, the sort of the all possible computations thing that is all sort of packaged up, of which in which we are kind of perceiving a piece of it. There's this question of for example, is an example of something you could think about is a given mind exists at some place in this rulad. It's a small thing in the rulad. It's not of the rulad is made of things we call eames, which are kind of the atoms of existence. A mind spans many atoms of existence, just like we are made of many atoms of physical atoms and molecules and things like that. We span many, many atoms of existence, but we're tiny compared to the whole rulad. A single mind is a tiny thing, and just as we are pretty small compared to the physical universe. But as we kind of sort of develop our civilization or whatever, we send spacecraft out, we expand our kind of footprint in the physical universe. There's an analog, which is to expand our footprint in the rulal universe, in essentially the universe of possible views of how you can think about the universe. And in a sense, as we expand kind of our way of thinking about things, our paradigms for viewing the world, we're sort of gradually kind of expanding. We're exploring more and more of rulal space, just as, we send out spacecraft, they explore more of physical space. So as we invent new paradigms for thinking about science or philosophy or whatever else, we're expanding in rulal space. So one of the things, sort of an interesting question is, well, what if we manage to really be successful at that? What if we manage to cover the whole rulad? What if we manage to expand so that our minds sort of cover the whole rulad? Well, it's a be careful what you wish for type situation, because in a sense, the fact that we coherently exist is a consequence of the fact that we're not everything. We are the small specific things that we are. We're not sort of we don't, if we covered everything, there would be nothing sort of coherent and special about us. And so in a sense, our nature as you can say conscious beings or whatever is a consequence of the fact that we are limited. We are these tiny dots in this whole kind of rulal space in the whole rulad. We are sort of tiny spots, as we are in physical space also. It's even smaller. Our footprint in rulal space is even smaller than our footprint in physical space. But it's sort of, in that case, you could say, well, can we reach the point where we have expanded so much in rulal space? One of the consequences is then in no sense do we coherently exist anymore. Our coherent existence as sort of, in a sense, individual special things is a consequence of that limitation of our extent in rulal space.
Wow, beautifully said. I also wanted to talk about intelligence. How would you, in your words, define intelligence when thinking computationally across humans, machines, and nature?
I think intelligence is a slightly less sort of problematic concept than consciousness. I think that it's one of the kind of features of intelligence is you have to be able to sort of work things out. You have to be able to compute things. You have to be able to sort of follow rules that have consequences and so on. And the fact is that one of the things that's sort of a piece of science that I discovered years ago now is this thing I call the principle of computational equivalence. People used to think that to reach a level of sophisticated computation, you had to go to a lot of trouble. You had to build a very special system. You had to build a computer, a microprocessor with millions of transistors. You had to set up some very complicated thing. One of the things that I discovered is that if you just start looking at the very simplest programs, the very simplest sets of rules, you very quickly get to ones that are as sophisticated in their behavior as any system can be. So in other words, it isn't the case that to reach this sort of level of sophisticated computation, you have to build this very complicated thing. Sophisticated computation is ubiquitous in the computational universe. And so that's this idea that sort of intelligence, the ability to do sophisticated computation, something very special, like very special about us, is just not true. It's something we see throughout the kind of abstract world that we can construct. We see it throughout the natural world. It's a very common thing. So now the question is that it's, the computation capability is there, but the issue is it an intelligence that's aligned with our intelligence? Is it something where, yes, it's doing lots of computation, like the waterfall I was mentioning before, it's doing lots of computation, but it's doing things that are not computation of the kind that we do, so to speak. So, when it comes to AIs, for example, the current round of kind of neural network, large language model AIs are pretty similar in architecture to brains. And they do things, their sort of form of intelligence is in some ways shockingly similar to what seems to happen in our brains. And so that's a place where we recognize sort of fairly aligned intelligence. If you think about sort of arbitrary programs, not programs that are specifically intended to be sort of aligned with the way actual brains work, you look at arbitrary programs, they do all kinds of things. They do very rich and complicated things, but they're things that are very alien to us. They are doing things that we can think of as being examples of intelligence, but very non-human intelligence, very intelligence, very, very, very alien to the kind of intelligence that we're used to with humans and creatures like humans or AIs built with humans as a model, so to speak.
Mm-hmm. Roger Penrose has long explored the idea that consciousness and even reality itself might involve non-computable processes, particularly in the context of quantum mechanics and his orchestrated objective reduction theory. Given your view that the universe operates through fundamentally computational rules, how do you reconcile or challenge Penrose's notion that certain aspects of reality might lie beyond computation?
I've known Roger Penrose since the mid-1970s. So, I think Roger is wrong about the need for sort of things beyond the physics we know to explain kind of the quotes phenomenon of human intelligence and consciousness. And in fact, I think that the last nail in that coffin is pretty much was pretty much hammered in by large language models and ChatGPT and so on. It seemed to be the case that there were things that were sort of magic that we humans could do that were beyond what we could expect computers to do. And it was kind of shocking that, you couldn't get a computer to tell a picture of a cat from a picture of a dog type thing. It was like these computers are kind of dummies. That's what Roger actually said at one point. Actually, I had the very amusing experience. My day job is being a tech CEO, trying to create computational tools for the world. And back many, many years ago, I was Roger Penrose had written some book about computers and about the sort of inadequacy of computation, explaining things. And the summary of this that I'd just seen was in Time magazine or something, was, computers are all dummies. And I was looking through the new people who'd registered our software. This is a long time ago when there were even still physical registration cards. And what should I find but Roger Penrose's registration card for our software? And so I was kind of charmed by the fact that,
Oh, wow.
as far as Roger is concerned, computers are all dummies, except he's still getting our software. So that's but no, more seriously, I think that the search for something beyond to explain the sort of the human experience is one that's existed forever. And I think that the lesson of science keeps on being, sorry, humans, you're not as special as you thought. Your planet isn't at the center of the universe. Your chemistry isn't anything that special. Your computation capabilities, as we now can increasingly see, aren't anything that special. Now, in some sense, then sort of where does that leave us as humans? Does that, I think that in a sense it is, then we realize that our sort of specialness is what matters, so to speak. The features that we have, whether it's the intelligence, whether it's the particular chemistry we have, and so on, all of this is somehow generic. But it's the particulars of the way that we are that, in a sense, are what's important about us. It's not, oh, we have this generic feature of intelligence. It's we have this particular intelligence that is human intelligence. But I think that the another perhaps irony of Roger Penrose's work is that the thing is sort of biggest achievement in science, probably are these things called the singularity theorems, which have to do with the inevitability of forming black holes. When you have enough kind of matter in the universe, you end up inevitably forming a black hole that is something that gets sort of separated from the rest of the universe. And in fact, in the simplest form of black holes, one feature of black holes is that time stops in a black hole. So normally time is just running forwards, and the universe is, as I would think about it, computing its next state and so on. But in the center of the simplest kind of black hole, time just stops. So in terms of computation, it's like there was a thing you were computing, and there was no more rule that could be applied to know what to get next. So it's as if you're simplifying some algebraic expression, or you're simplifying, 2 + 7 + 9 - 4, et cetera, et cetera, et cetera. You do the computation, and in the end, you get the number. I don't know what I just said, and I probably couldn't do the arithmetic anyway, but let's say you get the number 3 at the end. Once you've got the 3, there's no more computation to be done. And that's kind of what happens at the center of black holes, at least the simplest kind. So, in a sense, time stops. Now, the irony is that I think this orchestrated reduction concept, which is a slightly complicated concept, is actually the exact same phenomenon, but played out in a different kind of space than physical space. It posits, I think, the existence of what, in our view of physics, will be called branchial black holes that are not physical black holes. They're black holes that are kind of a place where time stops, but where time stops with respect to instead of the extent of physical space, the kind of the choices of quantum branches that you can make. It's a slightly complicated story, but perhaps the human irony is that I'm pretty sure that Roger has recapitulated his big science discovery of many years ago in his thinkings about quantum mechanics. I'm not sure it applies there, but it's kind of an interesting human point that I think it's one of those features of all of us, that there's a certain way of thinking that one has, and in the end one imposes that way of thinking on the things that one thinks about, and one can be lucky that way of thinking actually applies, or one can be unlucky that it's like, well, the world just doesn't happen to work that way. And I think that as I say, the search for the, in a sense, spiritual spark that goes beyond the mere deterministic scientific physics and so on, it's a continuing thing. I think there's sort of increasing evidence that isn't what's special about us, so to speak.
I also wanted to ask, how should we understand all the randomness in a fundamentally deterministic but computational universe? According to you, does free will exist, or is it an illusion?
Well, so what does free will mean? I mean, one imagines, if you look back at sort of early science fiction movies that had robots and early AIs and so on in them, you could always kind of tell the thing was a robot because its behavior was quite simple. It was following logic, and it did something, and then there was this kind of idea that if there were definite rules by which the thing operated, its behavior would somehow be correspondingly simple. So it turns out, as a matter of science that I guess I kind of discovered in the 1980s, that that's just not true. just because the rules for something are simple doesn't mean the behavior of the thing should somehow be correspondingly simple. It's possible to get immensely complicated behavior even from very simple rules. We don't tend to, in traditional engineering, we tend to build systems where we can foresee what they're going to do. So we don't end up building mostly systems that might have simple rules but have very complicated and very hard to understand behavior. So we're not quite as used to that. If we look around in nature, it's pretty common that there are rules that are quite simple, but yet the behavior is very complicated. So the first thing to realize is that the kind of notion that if you have deterministic and perhaps simple rules, that necessarily your behavior is very kind of clunky and very kind of old style robot, that isn't, as a scientific matter, that's not the case. So now the question is, well, what happens? Let's say your rules are deterministic, simple, whatever. Does that mean that in no sense do you have free will? Well, here's the thing. If one could readily say, I know what that robot is going to do, I know what that fruit fly is going to do, whatever, you can readily say it doesn't have free will because I can, whatever it's thinking, I can just jump ahead and I can say, I know what it's going to do. It's going to do this. And because I know what it's going to do, it's something where it obviously doesn't have free will because it has no choice. It's going to do that. Okay, so what happens when you have simple rules and you have very complicated behavior, there's a phenomenon I call computational irreducibility, which is a very important phenomenon. It shows up. I've sort of discovered it 40 years ago. I thought it was kind of neat. And it's over the years, it's sort of advanced in its importance in many, many, many different ways. But for free will, the importance is this. You might say, given that I know the rules by which some system operates, that immediately tells me everything about what the system is going to do. So even if the system itself had to go through 1,000,000 steps to work out what would happen after 1,000,000 steps in the system, I can, by knowing its rules, just jump ahead and say, okay, I know what the result is going to be. That's a very traditional kind of thing to want in exact science. It's like that's the big achievement, in a sense, of mathematical science, tends to be, I don't need to follow the Earth around 1,000,000 orbits. I can just write down a formula and fill in the number 1,000,000 and say where the Earth is going to be after 1,000,000 orbits type thing. I can jump ahead. I don't have to follow all the steps. Computational irreducibility says that for many systems, you actually do have to follow all the steps. So what does it mean if you have to follow all the steps? Well, that thing where you said it doesn't have free will because I know what it's going to do, you don't get to say that. The only way you can tell what it's going to do is to follow each step, which is the same as what it's doing. So in some sense, it's what it's doing. It's doing what it's doing. It's not something where you can point at it and say, aha, you're a deterministic system. I know what you're going to do. And so I think that's the sense in which we have free will, that we can't know in advance what we're going to do. Now, one day it'll be possible to kind of read out the states of all the neurons in our brains and so on, and to compute, what are we going to do next? But in some sense, the thing we'll be doing is just recapitulating what's happening in our brains. We're not able to just say, you don't have free will. It's like we can just go immediately to the end point, so to speak. So I think that's the and if you ask questions like, do AIs have free will? Well, the answer is in the same sense that we do. AIs similarly have free will. They similarly have this notion of irreducible computation. You can't know what the thing is going to do until it's done it, so to speak, and you have to follow each step. Now that means, for example, that if you say, well, I want to make sure that my AI will never do the wrong thing. Well, that's something you can't guarantee. You can't. To know what it's going to do and to know it will never do the wrong thing, you have to have kind of followed an infinite collection of possible steps it could have taken, which you can't get to do. And so that's sort of another consequence of this kind of computational irreducibility idea. But, when it comes to randomness, there are a lot of things where this, what randomness is usually, what do you mean by something is random? What you mean is you don't know what's going to happen. You don't have a way to kind of sort of say, I see a pattern, I can compress this, I can kind of summarize it in less, without giving all its details, I can know what's going to happen and so on. So, kind of the idea is one of the things that one sees is that it's surprisingly easy to make something which you can't predict. That's not something that, and often when one thinks about randomness in science, one is saying, well, there's a system that I'm looking at, and something outside the system is kind of kicking that system and making something, quotes, random happen. And I call it random mostly because it's something from outside that I don't know about. Well, my guess is that, in fact, I know from many cases that a lot of things that we've just said, oh, it looks kind of random. It's not random in the sense that there is no rule. It's random in the sense that that rule is not something that we, as observers that are as sort of limited as we are, we can't kind of unravel that rule. The system itself might have very simple rules, but when you apply those rules many, many times, the results you get are something you can't get without applying those rules many, many times. And that requires an amount of computation that's much greater than we can kind of muster. I mean, a very well, for science, for physics at least, an important case of this is the second law of thermodynamics, the law of entropy increase, which says, if you have a bunch of gas molecules and you start them off in some very orderly pattern, they will tend to get to a pattern that seems quite disordered, that seems kind of random. What's happening there is something like what happens when you encrypt a message. It's like you started off from that very easy to understand configuration of molecules, and then this process of the molecules colliding with each other and so on, that was an irreducible computational process that effectively encrypted the original message. And we, as observers of the kind we are, sort of minds of the kind we have, are just not capable of decrypting that message. It's something, and so to us, we just say it looks random to us. Now, I will say there's another wrinkle to this whole thing, which is in quantum mechanics, in physics, sort of the big thing that happened basically 100 years ago this year, more or less, was this kind of transition to a belief that sort of underneath physics, there was this other layer of quantum physics, and kind of the big characterization of the classical physics versus the quantum physics is in classical physics, in a first approximation, you do something like throw a ball, it goes in a definite path. In quantum physics, it's more like you throw the ball, there are many, many paths that are followed, and we only get to say what the probability of what happens is. So quantum physics is all about many paths of history being followed. We now understand with our physics project in recent years, we now understand a lot more about the literalness with which there are sort of these many threads of history that occur in physics. And so one of the questions is, one question is, if there are many threads of history, why do we think that definite things happen? And that's very related to this thing we were talking about before, about the fact that human consciousness follows this single thread of experience. We force the world to be such that we perceive definite things to happen. Just as we might say, there are all these gas molecules or they're all water molecules in some water, but yet what we perceive is that the water is flowing in a definite direction, even though if we were to look in more detail, we'd see all those molecules going in all these random different directions. So it is a feature of observers like us that we aggregate many threads of history together in what we perceive to be what's happening in the universe. Now, one tricky thing is that one of the big features of quantum mechanics is there seems to be some sort of intrinsic randomness to it. It's like you do these different quantum measurements and you'll get an answer that's kind of, it's random. It doesn't, you don't seem to be able to determine what the answer will be. I think the way that works is in the rulad, there are many, many possible threads of history, and they lead to all sorts of different answers. But we, as observers of the rulad, are localized. So for us, there are only particular threads of history that we follow, and so that's kind of our choice. You could have all these different possibilities, but the choice that we perceive is the one that we are sort of at that place in roughly in rulal space, more precisely in what we call branchial space, which is a subset of rulal space. But in any case, our existence is just as we're at a definite place in physical space, so we're also at a definite place in rulal space and branchial space, and that causes us to perceive a particular history, or a history like that is close to a particular history and not another one. And so then one of the things that is remarkable is that in that situation, we humans believe in objective reality. We believe that definite things happen. And I think the reason for that is that all of our minds are pretty nearby in rulal space. So let me give an analogy. So let's say you're saying, what is the configuration of stars in the night sky? So basically, people who are on the Earth will all pretty much agree. What's maybe different places on the Earth, they'll have slightly different answers, but basically they'll agree. What's the configuration of stars in the night sky? But to some, alien living in another galaxy, the configuration of the stars in the night sky is completely different. But yet, if, for all of us humans, we're all on the same planet, so we all look up and we see the same night sky. So it is, I think, with the kind of randomness that shows up in quantum mechanics, we all are sufficiently close in branchial space. All of our kind of where we are in branchial space is close enough that we basically perceive the same phenomena going on in branchial space. If we could imagine sort of aliens who were living somewhere different in branchial space, and they would perceive a very different set of things to be what's actually going on. So I think that there is, in a sense, you can say there's randomness because there are all these different possibilities laid out in branchial space. But for us, we all agree about the fact that we got this particular one because this is where we happen to be in branchial space, just as the night sky is the way it is because this is where we happen to be in physical space.
Thank you for that insightful explanation. That it really does make sense. And even like you said about the randomness, that it's just our kind of limited nature of as observers that we perceive it to be random. But yeah, so great way to put it. I also wanted to talk about your integration with Wolfram's Alpha and ChatGPT. According to you, how do you see Wolfram Alpha's integration with ChatGPT shaping the future of hybrid intelligence?
Well, I mean, look, what neural networks and LLMs and so on do well is a bunch of things that we humans also do pretty well. You can do things that, like telling cats from dogs or making up English sentences or whatever else. These are things we humans do sort of effortlessly. The thing that happened the last 300 years was we humans built a different way of doing things, which is we built kind of formalism in mathematics, in logic, in computation. We built this way of systematically doing things that is very different from what we do in our minds. If you say to somebody, run a program in your mind, I don't think anybody can do that. We're not built to do sort of deep computation in our minds, but we have built machines that can do deep computation. And that's kind of what I've spent a large part of my life, is building that kind of machinery to sort of represent the world computationally so that you can build these kind of formal towers about all sorts of things in the world. And so what we see is our Wolfram language and Wolfram Alpha and so on. It's making use of this kind of computational formalization of the world. And that's something where, just as humans for the last, 38 years or something, have been using our technology to discover lots of things in science, to do lots of things in engineering, to run companies, all this kind of thing, just as humans have been using those capabilities to do that, so now the AIs need those capabilities as well. The AIs intrinsically are doing the kinds of things that we humans intrinsically do in our minds, which doesn't happen to include this kind of structured, run the program in your brain type thing. And that's what we're providing. And it's been really kind of interesting. I mean, I didn't see this kind of integration coming. For years, we've had lots of wonderful human users of our products. In modern times, we're also having an exploding number of AI users of our products, where the AI is going along, and a typical kind of thing is the AI will be going along making up some statement, and then it will formulate a question, and it will send that question to our technology stack, get the question answered, then the result of the answer to the question will become kind of part of the prompt for what the AI goes on to say, so to speak. So it's kind of like the AI has a neural implant that is our computation capability, and it's thinking along in its normal way, and then it's kind of asking its neural implant, okay, go compute this thing for me, and then you get back the results. It'll be interesting, maybe humans will be able to do that directly too. Right now we're stuck doing that by typing with our fingers and so on. But it's sort of the same idea. So I think that's what I think sort of AIs, LLMs, and so on provide very well in the textual domain, for example, is this sort of layer of linguistic interface, this ability to kind of go from human conversation to something that can be sort of extended. And now what we're seeing is they also provide an interface to this layer of computation that we've been building for such a long time, and that's a cool thing, because the whole idea of Wolfram language is to have a computational language to talk about the world. So, for example, when there's sort of been a series of efforts to formalize the way one talks about the world. Even human language is in a sense a way of formalizing the way you talk about the world, because you could say, I'm going to point at these different, snakes, and then you can say, point at these things, and then we say, well, they're a snake. So then you have this sort of way of collectively referring to all the things that are like snakes. And so that's sort of one level of formalization. Then we have things like logic, which is sort of another level of formalization. Then we have mathematics, another level of formalization. Then we have computation. And computation, and what I've tried to do with computational language, is a way of sort of formalizing the way you talk about the world, whether the thing you're talking about is an image or a city or a chemical or a star or whatever else. This is a way of kind of talking about those things computationally, being able to take sort of the knowledge that we've accumulated as a civilization, make use of that in computing things about the things you're talking about. And so my big effort has been to sort of develop this formalization of the world, computational formalization of the world. It's kind of, an analogy, I suppose, a weaker analogy in some ways to what I've been trying to do. It's about 500 years ago, people invented mathematical notation. Before that time, if you were talking about math, you were using natural language. You were using ordinary language words to talk about math. And then things like plus signs and equal signs and all those kinds of things got invented. And that was a pretty big deal, because it allowed one to streamline one's talking about and thinking about math. And that's what got algebra started, and then calculus, and basically all of the modern mathematical science was started from sort of inventing that notation for talking about mathematics in a streamlined way. And what I've been trying to do for the last, 40 years or so with Wolfram language is to build that same kind of notation, a computational notation for talking about the world, a kind of computational notation that allows one, that you can think in and think about the world in this sort of formalized computational way, and also, by the way, get a computer to actually implement and go from sort of an idea you have to something that the computer can then work out automatically. That's kind of the pattern. And I mean, what we see right now is that what has been the case is for people to use our computational language. I mean, just in our world, there are sort of two different branches. One is Wolfram language, which is this formalized computational language for talking about the world computationally. The other is Wolfram Alpha, which is a kind of consumerized version of that, where you're just sort of typing or saying natural language, and you're asking sort of small questions. With Wolfram language, you can build up sort of giant capabilities. People write, million-line programs that run large organizations and things like this. With Wolfram Alpha, you're dealing with, I've got a specific question, it's one sentence, that's what I'm asking. So the thing that has been the most powerful thing is the Wolfram language, computational language. And that's been something where you kind of have to learn that language to converse in it. But now that we have this kind of linguistic interface layer, it's courtesy of LLMs, we can kind of open that up, and it becomes much more possible to just have a very vague idea, have that sort of crispened up as something formal and computational by our notebook assistant, as we call it, and then from that build up this sort of formalized Wolfram language representation that you can then compute from and think in terms of. So it's kind of our picture, and it's kind of it's sort of an exciting thing because I've been building in this direction for a really long time, and it's kind of the way the world has evolved and the way sort of AI technology has evolved and so on. It just arrived in right the place where we can make use of all the stuff I built for such a long time, which is really cool. I thought we'd only have human users. I didn't think we'd have AI users, but now we have lots of AI users.
Yeah, no, it's very exciting. And I wanted to ask you, according to you, um, how can users learn to think with these intelligent systems instead of just delegating thought to them? And then what's the next major leap you'd like to see in how humans interact with computational knowledge?
So I mean, the the paradigm of the 21st century is basically the computational paradigm. That's, if you want to sort of if you want to advance in whatever field you're doing, it's like there's this idea of computation, this formalization of things in terms of computation, and that's where you kind of get lots of power. It's sort of this superpower of being able to represent things in computational language, use the computational language to actually figure things out, and so on. So how does one get there? Understand computational language, understand the kind of computational way of thinking about things. I think, the things I built are sort of the best effort we have, so to speak, at providing kind of the language that to learn to think in terms of. Beyond that, it's kind of like, how do you learn to think computationally about things? Well, it's pretty worthwhile to know the facts of how one has been able to make lots of things computational, whether they're sort of representations of food, or whether they're representations of sounds, or different kinds of things. Each one of these has a way to sort of formalize it to make it computational, and understanding how that works and what kinds of things you can do computationally, that's really valuable. And I think, my usual statement is that for any field X, from sort of archaeology to zoology, there either is now or soon will be a computational X, and that will be the future of that field. And so that's that is the great paradigm of the 21st century is this computational paradigm, this way of going from of formalizing things computationally, and then getting computers to actually help you with that formalization and take it to places where you as an unaided human would never have been able to go.
Wow. For everybody watching, for the audience watching this podcast until this point right now, can you share some of your personal philosophies or daily habits that help you sustain curiosity and deep thinking? And personally, do you find more meaning in discovering universal truths or in creating systems to explore them?
Let's see, you asked many different things there, but let me try and unpack that a bit. I mean, so, I alternate between doing basic science and developing technology. And that's been a really powerful thing in my life, that I built technological tools which have allowed me to do basic science. I've understood things from basic science that have allowed me to go on and build technological tools. And I've kind of done, I don't know, about 5 iterations of that kind of cycle between basic science and technology in the course of my life. And that's been a really powerful thing. Now, what do I like better? Building technology where you're just creating something from nothing, or doing science where, in a sense, the world is the way it is and you're trying to figure out how it works? For me, those two things are closer than you might expect. So I see kind of technology development as there are certain things you want to do. Now you have to kind of drill down to understand what the essence of those things is. You have to almost do a sort of science of the technology to understand what is the essential thing I should implement in my language or whatever else to be able to let people do all these kinds of things. It's just like, what is that thing made of? Is it made of atoms? Is it made of atoms of space or whatever else? It's very much the same type of thing at that level. And similarly, on the scientific side, a lot of what I've done has to do with, well, imagine we have this abstract object like this. What are its consequences? So that's again, it's sort of both sides of the kind of technology and science end up being much closer together. I mean, for me personally, I think my main skill is being able to take, fairly complicated things and sort of drill down and understand what the foundations of them are, what the essence of what's going on is, and then often take that foundational essence and build up from there to more sophisticated science or to technology that people can use and so on, to do, in a sense, when it's technology, we call it engineering. When it's science, we still call it science, but building up from the underlying principles to the kinds of things that are sort of human accessible, so to speak. So I think that for me, that's the main thing that I like to do. I like to understand things at some sort of fundamental level, and that turns out to be important in technology as well as in science. And I like to build things from those foundations to things that are readily usable, which again turns out to be sort of the same kind of story in technology and in science. I think it's somehow, well, so in terms of, my personal habits for things, I don't know, I've been lucky enough to be able to do stuff that I find pretty interesting most of my life. And, that's I am, I suppose, lucky that there are just, every time I figure out more stuff, I realize there's more stuff to figure out. And usually I'll have projects which sometimes I've been thinking about for decades, but the world isn't quite in a state where, it's worth really diving into that thing. There's too much sort of infrastructure that needs to exist in the world for, and until it exists, it's not worth me trying to do the thing that I want to do in that area. So that's a kind of a typical pattern for me, is that I'll be thinking about things for a long time, and then the world will get to a point where, or my understanding will get to a point where I can dive in and do something. I was doing that in the last year a bunch in kind of foundations of biology and so on, understanding how biological evolution works, something I had thought about in the 1980s, didn't make that much progress with, had been kind of accumulating knowledge about ever since. And then finally I realized sometime last year, gosh, I actually can see what one can do with this, and then made a bunch of really nice progress in that area. I mean, in terms of my, one of the things I've tried to do is build tools so that I can do what I want to do as efficiently as possible. And those tools are to some extent technological tools, of building Wolfram language and so on. To some extent, they're human tools. I built a company that takes ideas I have and helps turn them into real things. I built kind of a personal way of working that is quite efficient in terms of me being able to go from an idea to a real thing, or to the working out of that idea. And I think, I tend to be, I like to automate things. I like to take it from the point where I have to do this by, I'll do it myself a few times, and then it's like, wait a minute, I can just write a program to do this, or I can build a management system that can get this done, so to speak, in a way that is, at least with respect to me, automatic. And, I find that in my general life and times, I lead, in a sense, a simple human life, but a complicated intellectual life, so to speak. I eat the same thing for breakfast every day, but yet I think about different things every day. So it's kind of and I find that when the things that I think about end up, as I say, producing more things to think about. I also find that another aspect of the way that I work is I like to explain what I'm doing. I like to, write things that explain what I'm doing. I like to, do live streams that explain what I'm doing, these kinds of things. Partly because that helps me to actually understand what I'm doing myself. If I can't explain what I'm doing, I don't really feel like I understand it. It has the side effect that other people can kind of share the fun type thing of understanding things. But for me, the act of explaining things is important as a way for me to drive my understanding of things. And that's been kind of another sort of personal aspect of how I've been able to make progress in both science and in technology.
Well, Stephen, Thank you so much for your time. It's truly been an honor having this insightful conversation with you. I'm really looking forward to see Wolfram Alpha's integration with ChatGPT and how it shapes the future. And yeah, I'll hand it over to my twin sister now to continue the podcast with her segment.
Hey,